Technology, Burla. Now I'll request Dr. Kaushik Mishra to introduce to give the brief introduction regarding our speaker or expert today. So Dr. Kaushik Mishra, please go ahead introducing our speaker to the audience.
Thank you so much, sir. First and foremost, a very good evening, ladies and gentlemen. This is Dr. Kaushik Mishra, welcoming you all to the fourth day of AI/ML FDP program, jointly organized by ODIAS in Machine Learning and VSSUT Burla. It's my immense privilege to introduce our guest speaker for this session, Dr. Erion Çano. Dr. Çano is currently working as a postdoc at the Digital Philology Lab at the University of Vienna. And he's the principal investigator in the project titled Cognitive Plausibility of Deep Learning Language Models, which was granted by the Austrian Academy of Science. Dr. Çano was previously a postdoc in the field of text summarization at Charles University, Paraguay, Czech Republic, and obtained his PhD in sentiment analysis from Politecnico di Torino, Italy. His domain of research includes deep learning for NLP and more precisely understanding human cognition mechanisms and performing text summarization and generation as well. He also has early career experience in software development as well as teaching experience in several universities. It's my immense pleasure to welcome him to this very session. Ladies and gentlemen, please welcome Dr. Erion Çano. Over to you, sir.
Thanks a lot for the introduction. And welcome everyone to this presentation. It's my pleasure to present to this event. I hope you can hear me well. So please confirm, like, can you hear me correctly?
Yes. It is audible. You can go ahead.
Thanks. So yes, once again, it's my pleasure to present in this event about text representation and language models and several very recent developments in the field of NLP and computational linguistics. So yes, I will start my presentation.
You please unmute yourself.
Now I hope you can hear me now, right?
Yes.
So thanks again for attending this presentation, and here is an outline of the topics that I will be speaking today. So I will start talking about traditional text representation models like the vector space model for text representation and its problems, its drawbacks. Then I will switch to more dense representations like the word embeddings and their advantages. I will continue with some specific word embedding models like the SIBO, skipgram, FastText, and their specifics and their let's say advantages over the vector space model. Then I will talk about some ways that we can use, some methods that we can use to make let's say utilization of these word embeddings in our downstream tasks, NLP tasks, like topic recognition or sentiment analysis or question answering on other tasks. And then I will illustrate this with some code snippets that I prepared, how we can train the word embeddings and what kind of predictions can we make with them. I will continue with pre-trained language models, which are very recent developments, like significant advancements in the field of NLP, natural language processing. And then I will conclude by introducing BERT and some of these variants that are, let's say, the cutting edge models that are used today. So now here, let's start with the vector space representation. It's a traditional representation model that is theoretical, that is basically simple, like based on the notion of multidimensional spaces and vectors. It has been used for quite a lot of time, but in the recent years, it was obviously replaced by the other dense representations. So now, how do we represent text? So our common, let's say, problem is our common scenario, let's say, is to try to train some model in a certain data set that we have, and trying to have the model make some predictions. So let's suppose that we have a collection, a data set of, let's say, plays by Shakespeare. Here we have some plays: Antony and Cleopatra, Julius Caesar, Hamlet, Macbeth, Othello, etc. So this is a collection of documents that we have. And all of these documents have text like words, sentences, paragraphs, etc. And our main problem, the first, let's say, challenge that we have when working with text is how to encode it. Same as with video, same as with images. So we need, let's say, a way to encode text so that the computer recognizes the text, and then all of the methods that we use can process it. So let's say that the first, one of the earliest this text representation models was, as I said, the vector space representation that is based on the idea that each document should be modeled as a vector in a multidimensional space. And then we have these words that are inside a document that are considered as features. So now, normally, when we have a lot of documents in the collection, they will contain different words, and all of these words make up the vocabulary of the language in which these texts are written. So normally we have text in English, supposedly, and they will cover all the words, let's say, form a vocabulary of the entire collection. So let's say if we write the vocabulary as V, and then the module of V will be the number of unique words that we have in our entire collection. So now in these slides, I'm illustrating a very minimal example. So I'm giving you a very minimal example, and we suppose that the vocabulary here, like the size of the vocabulary, is only 7. So we have only 7 words in this collection of 6 plays by Shakespeare. So we have the words Antony, Brutus, Caesar, Cleopatra, Mercy, and Worcester. So we have, let's say, words of names like proper nouns, and some general words like Mercy or Worcester. And so now here, the dimension of the space that we will use to represent these documents is only 7. So it's the same as the unique number of words that we have in the collection. So now, and is a component of the vectors of the respective vectors. But there are some, let's say, more advanced representations of the same model that add also n-grams, like add word combinations, like say b-grams, like 2 combinations, 2 consecutive words, or 3 grams, 3 consecutive words. And they add them in the representation to enrich, let's say, the representation. And now here in the previous slide, here we have only a binary encoding, in the sense that we use only zeros and ones. And a 0 in a certain document and word indicates that this word is present in the respective document. A 1 indicates that the word like Brutus, for example, is present in Julius Caesar, because there is a 1 in the cell in the row column intersection. And the 0 indicates that the word is not present in the document. So besides using the discrete, the binary representation, we can also convert these zeros and ones. So we can use some weights to have, let's say, some more significant numbers. And the weights normally try to, let's say, a more relevant representation when it comes to which, let's say, terms pertain to certain documents. So let's say, so this document term matrix is formed, like we see here, the matrix. Now here, this matrix is 6 by 7, because we have only 6 documents and 7 unique words, like the vocabulary, the module of the vocabulary is only 7. There were some developments, like trying to improve this representation by using matrix factorization techniques, trying to optimize it. And something good about this representation scheme is the fact that we can apply, since we represent the documents as vectors in a multidimensional space, we can use our knowledge from mathematics, from algebra, to perform operations on these vectors, like, for example, to compute the distance of this matrix, of these vectors, of all of different possible vectors. And the distance will indicate how, let's say, how much these vectors are similar or dissimilar with each other. Or we can also compute similarity, like cosine similarity between two vectors from mathematics. We know it, and it will indicate, let's say, how close are the two documents with each other, how similar are with each other. But there are still a lot of drawbacks that have been observed during the years by using this, let's say, representation scheme in different tasks, downstream NLP tasks. One of the biggest problems is the fact that this scheme is doesn't scale well with when it comes to the vocabulary, so it has a very bad scalability when it comes to vocabulary, because when the collection of documents becomes big, the terms that they will contain there will be more and more unique terms that will contain it, which means that the vocabulary of this collection will be very big, like hundred thousands of words. Like if we have, let's say, today databases of today contain hundred thousands of documents that are of different lengths, and normally they cover the entire vocabulary of English language, for example. So the matrix becomes so big. And we have also this other drawback, that is the fact that the matrix is very sparse, because we know that a document can contain, let's say, 100 terms or 200 terms or 300 terms, and which is much smaller than the entire vocabulary, like 100,000 of terms. So we will end up with let's say, a matrix that has many zeros and only a few ones in some positions, right? So only a few ones for the words that are included in a certain document. So this is another big drawback of this scheme, representation scheme. The fact that this matrix is huge becomes very big. So here in the rows, we will have hundred thousands of documents, and in the columns, we will also have like hundred thousands of unique terms that will make up the vocabulary. So this matrix will be huge and very sparse. So the sparse, yes. So this is one of the other problems. And another problem is the fact that it's hard to perform feature selection. So now in this representation scheme, the vocabulary, like all the terms of the documents, are features. Are characteristics of every document that can be used to represent the document. But the problem is that we don't want all of the features. We want only the features to work with only the features that are very relevant, that are very good representatives of a document. And performing this feature selection becomes also very hard because of the high dimensionality of the vectors. Like the vector space becomes very huge, very with high dimensions, and it's very hard for us to perform the feature selection process, like to try to spot and select only the relevant words from the entire vocabulary. And another drawback was the fact that since this representation is sparse, it doesn't work. It didn't work well with the neural networks that were surging in NLP. The neural networks started to become very popular in 2010, 2011, and later. And it was obvious that this representation scheme was not compatible with neural networks. So for this reason, like so as I said, like there were some attempts to let's say to alleviate these drawbacks of the vector space model. For example, to alleviate the sparsity, the high dimensionality of the matrix, of document term matrix. There were some researchers that tried to use knowledge from linear algebra, like matrix factorization, to try to factorize this big matrix. So once again, here we have this X, the matrix that we're of the collection that we try to represent. So it has M samples, the documents, and each of the documents has n dimensions in the vector space, like in n-dimensional vector space. So this M and by n matrix is very big and very sparse, right? So that was one of the main problems. So one of the ideas was to try to factorize it, to represent it as a M by K matrix multiplied with K by N matrix, and so that the X, the big matrix S, is like W times H. And these two matrices are significantly smaller, So the M by K is smaller, and K by N, they are much smaller than the M by N matrix. But if multiplied, they somehow give us back the original X matrix. So when we want to work with this X matrix, we actually work with the two smaller matrices, keep them in memory and process them. And so it's like let's say it's easier to work with. It doesn't take all of the resources that we would use with M by N matrix. So this was a kind of improvement, but still it was not a very significant improvement. And since the problem was
Dr. Çano, I think you are muted. Your voice is not audible.
Like there was a. Is there okay? Is it okay now? Can you hear me now?
It is fine now. It's fine now.
Okay, thanks. So there was a disconnection. So I was trying to say that there were some, let's say, there were some ideas by linguists which motivated the need to, let's say, switch to some other representation scheme, like to go away from the vector space model. Because another drawback that I forgot to mention of the vector space model is that the vectors that represents the documents are orthogonal to each other and do not share any information, right? So a word, let's say Julius Caesar or Brutus or something, they are completely different vectors in our space, in the vector space model. And because of this fact, they do not share any information. But from language, from the linguistics, we know that some words are synonyms with each other, especially some words that that appear near each other, right? Here we have two examples, like we have cucumber, sauce, pizza, ketchup, and they are, let's say, indicate, they always relate to the word tomato, right? Because we have tomato ketchup, tomato sauce, or pizza. So also, like another example, soundtrack, lyrics, sang, duet, they are somehow related to the word song, right? So when we use the vector space model, we do not account for these analogies, these similarities of the words, and they are just represented as completely different vectors, orthogonal vectors in the vector space. So this was another motivation from switching from let's say going away from the vector space model and trying to find some other representation models that I will try to cover now. I will explain now. So yes, these were the two linguists with their citations, like words that occur in the same context tend to have similar meaning. So the idea of context. So if we have words in text that are near each other, they have some meanings, they share some meaning with each other. So we have to account for that, right? Or let's say almost the same thing expressed in a different way. You shall know a word by a company, the company it keeps. So the company it keeps are words that are near that word, let's say our tomato, for example, tomato. So some words that appear together with tomato are cucumber, sauce, pizza, and ketchup. So they share some meaning, right? Semantic value. So this word, let's say some motivation, linguistic motivations for developing the word embeddings. So now I will try to explain the concept of language model. What is a language model? So a language model from the computational linguistics perspective is a function that we try to learn so that we can use this function to assign probability to sequences of words in a natural language, right? So a sequence of words can be, for example, a phrase like cat sat on the mat, right? So this is a sequence of words. And the language model is a function that gives us the probabilities of these words coming together one after another. So probability of mat coming after cat sat on the, for example. Now, theoretically, these probabilities are chain probabilities, conditional probabilities, like the probability of mat given like with the condition that we have already saw cat set on the. And since the sequences of words in natural languages can be long, these probabilities are very long also and hard to compute. But there is still this Markov assumption, an assumption that tells us that the probability of the words only depends on a limited number of consecutive words, not on all the sequence length. Like if we have 100 sequence sequence of 100 words, then the word 100 doesn't depend on all the previous words, but only on n of them, only on a limited number of left words, let's say. So this is the Markov's assumption. And with this assumption, we can compute the conditional probabilities of a sequence. Like, for example, we have the sequence W1, W2, WT. We can compute it as a product of these probabilities, conditional probabilities of WT given n consecutive words. So not all the sequence of words, but only a limited number of words. Let's say 5 or 10, let's say, previous words. WT time t minus 1, t minus 2, t minus n plus 1. So this is the window that we can use to compute these conditional probabilities. So here, as I said, like I mentioned the example, cat sat on the mat. We can use this language model, let's say, to compute the probability of the word mat, given the words, like the previous words, cat sat on the. Okay, so now our objective now is to use is to train to instead of the vector space model with the vectors, the big vectors, let's say, and sparse vectors, we will now try to find out some vectors that are dense, that represent the words of a language, but are dense, that have a dimensionality that is significantly smaller than the big, the big matrix that we had in the document termed representation. So we will try to compute these vectors wi and vi that are, let's say, in RD, in the sense that are, let's say, of d dimensions. And this capital D is a relatively small number, like 100, 200, 300. Let's say this is what the number of dimensions that you would like to have in our representation of the words. So we can, let's say, have two types of words. W is a word that we are trying to predict. It's vector, like we are trying to learn its vector, and its vector is in RD, like a d-dimensional vector. And we also have other words that we have already seen, like we denote them with V, we write them with V, VI, are the words that form the context of the word of the unknown words. So V is the word that forms the context, and W is the word we will try to learn. So now our objective will be to have these probabilities, to compute these probabilities of ij. Ij are two positions. So the word in position I, we will try to find the probability of observing the word in position I, given the word in position j. So we will try, let's say, to compute a function, to learn a function that gives us these probabilities, and it's a function of these two words, like the vector w that in position I, that is the word, is a word that we try to compute, the vector we try to compute, and another vector of the word v in position j. So the word embeddings, let's say the methods for learning word embeddings are actually methods for computing this function, this f function that relates the different words. So now another trick that made it possible to learn word embeddings was the idea of negative sampling, which is also known as noise constructive estimation. So now, until now, we talked about language models, right? So all of these probabilities are about language modeling, like probabilities of finding sequences of words or probabilities of finding a word given some other words. So these are the language models, the traditional language models, let's say. But since the objective was to train the word vectors, it was not really necessary to go on with the language modeling. And the researchers who developed the methods for the word embeddings put this noise sampling idea into practice, and let's say moved away from the objective of learning language models, but their idea was instead predicting the probability of distribution over a certain limited number of words, not the entire vocabulary of a language, and make decisions like binary decisions for a certain number of words. And one of the decisions, for example, that was used was the idea of having this positive training set, which is a collection of words and sequences of words that are real from a language, that are in a data set, in a corpus that we have, and that are meaningful. Let's say cat set, for example. Cat set on the is a meaningful sequence. So let's say finding bigrams in this positive training set, and then also another set of sequences or phrases, but that is not real, that is synthetic, let's say, and not meaningful. For example, cat dirty. So if we have a subject and then an adjective, it's not really realistic, because we don't really see it. Like cat dirty is not a meaningful bigram, but cat set is a meaningful bigram. So the idea now was to try to, let's say, classify these bigrams as being in a positive set, in a real set of words, or being in a negative set, which is not a real set of words, but is a fake set of words. And this fake set of words, negative training set, was obtained from the positive set by using some manipulations. For example, we can use random transpositions of words, like instead of cat set, instead of set, putting the word dirty, for example, replacing it with a different word, or permuting the positions of the words. So if we do these transformations in the positive set, we get a negative set that is not a set of, that is synthetic, not a real set of a natural language. So this was the idea of negative sampling. So now here we have the likelihood. So the likelihood is our expectation of a certain probability. So we have two likelihoods now, two expectations. The probability of a bigram, let's say, with two words ij being in the positive set. So the probability of having a wi and vj appearing in the positive set. For example, cat set is in the positive set. And the other one is the probability of a certain bigram not being in the positive set, but being in the synthetic set that we artificially created. Like, for example, wi prime and vj prime. For example, cat dirty. Cat dirty, the probability of cat dirty being in the negative set. So now, if we try to compute this positive probability, that will be, let's say, an activation function of these vectors, then the negative probability will be 1 minus that probability, because one of the phrases is either a positive set or in the negative set. So if we compute the probability of that phrase being in the positive set, then we actually also have the probability of it being in the negative set. So this was the let's say, the training objective using the negative sampling idea. And here we have the maximization objective of the neural network that will try to compute this let's say, probabilities. So we have this likelihood, which is let's say a score that we will try to compute to maximize. So in the training of neural networks, we try to maximize this likelihood, which is actually a product of these probabilities. Now here we have y, and y is a label, is 1 or 0. If is 1, if the x that is a word pair, let's say, is in the positive set, given this parameter theta of the neural network, and 0, the yi will be 0 if the prediction is that this x, let's say, bigram or phrase is in the negative set. And normally we will try to maximize the neural network that we will train. We'll try to maximize this likelihood. But practically in the neural networks, it's better to try to minimize the log likelihood, actually, because it's simpler. And when we put the logarithm in this expression, we instead of computing the products of probabilities, we just compute the sum of the logarithms, and working with the sums is usually easier. So that's why we use the negative log likelihood. So now the objective will be to minimize the minus sigma of this logarithm of these probabilities, like yi, that is the prediction that we make, 1 or 0, which is a positive training set or negative training set, given this phrase xi, bigram, let's say, and the parameters of the network. So the parameters that we will learn from these predictions. And so, as I explained, that xi, I told you, is the word pair, like a bigram, from the corpus, or from the random, like from the positive set, that is the real corpus, or from the negative set, that is the synthetic corpus that we created. Yi is the label, 1 or 0, and theta is the parameters, like the parameters that are the vectors of the word that we will actually learn. And here we have the probability, like the logistic sigmoid. Sigmoid is the function, is logistic function that gives us a 0 or 1, depending on the probability that it is. So this WTV will be a probability. And that if that probability is higher than 0.5, the sigmoid will give us a 1, like prediction 1. And if this probability is smaller than 0.5, so it's from 0 to 0.5, it will give us a 0. So this sigmoid is a function that transforms the probability in a category from 0 or 1. So this will be the objective of the neural network. And then there are some other tricks, let's say, about some other tricks that the authors of word embeddings used. So they use these perturbations that I already mentioned to create the negative set, and they also observed that the negative set is it's better to have a negative set that is bigger in size than the positive set. So that is the same, like 1 time is the same, but it's bigger up to 20 times. So practically it was better, they observed, to have, let's say, a negative set that is like 10 times bigger than the positive set, using different manipulation techniques, different perturbations. And actually the negative set is usually constructed during the training. So since we train the neural network with batches of samples, so with batches from a positive set, so when we get a batch from the positive set, at that moment we can also create the negative set per batch, like we construct that batch of the negative set with those perturbations that I mentioned. So now, given these conditions, like this situation, this scenario, let's say, there were different possibilities how to train the neural network. like with what objective to train the neural network that will compute the probabilities and the word embeddings. So one idea was to try to use different, to learn different word combinations in a context window. Let's say one position, for example, we can learn one position, we can learn a word, we can, from the target word, we can learn one position left to it. Like we can compute the probability of WT minus 1 given the word T. So given the word WT, like the target word, we can compute the probability of the word before, left side. We can also do the same with the word on the right. So WT plus 1 given WT. We can compute two positions before the target word, like WT minus 2, etc. So we can compute different positions, let's say. And one idea was to use this window of size C words that are to be to form the context of our of our word, target word, let's say. So this was the idea of skipgram. So trying to compute, let's say, from a certain target word, try to compute its context, like the words that are in the left and some words that are in the left, C words that are in the left, and C words that are in the right. So formally, we can write this as the probability of observing WT minus C, T minus C minus 1.
अब हम साथ में खेलेंगे.
Yep. Please continue, Doctor. Actually, yeah.
Okay. Okay. So I was saying, you can hear me, right?
Yes, yes, yes.
Okay. So I was saying that one objective, like of the method called skipgram, was to compute these probabilities of the context window. So probabilities of C words in the left of our target word and C words in the right. So WT minus C, WT minus C minus 1, WT minus 1, and then the words on the right, WT plus 1, WT plus 2, WT plus C, given the target word that we have. So the condition is that we have seen a target word, and our objective is to compute the probability of the context window. So formally, this is written as this, like the P, the product of these probabilities from minus C to C of the target word T plus C, WT plus C, given the context, target context, and the target word WT. And normally we have the whole corpus have n, let's say, pairs, if we compute bigrams, or n sequences of words. So the total, let's say, negative log likelihood that we will try to minimize is all of this expression here, like the sum over n, and the sum over, so we will try to go left to right to all the sequences of words that we have, and we will compute these context windows, probability of these context windows. And so since we use since we use negative sampling, we will have this collection of m, let's say, for every, let's say, positive word in the positive set, we will have m negative words. So the whole expression will become this expression here that we will try to compute with our neural network. So this was the objective of skipgram. So this is the image representation. So we have the target word WT here, the embedding of the vector of this target word, and we will try to compute the probability of the context window that I explained. So the different words like WT minus 3, WT minus 2, WT minus 1, WT plus 1, WT plus 2, WT plus C, like an entire context window that we will try to predict. Now, another method with a different objective was called CBOW, continuous bag of words. So it's the same as skipgram, but the objective is the opposite. So now, instead of predicting the context from the target word, we will suppose that we know the context of a word, like the different words that come to the left of it and the different words that come to the right of it, and we will try to predict the target word. So in other terms, we will try to compute the probability of the target word WT, with the condition that we already observed the words T minus C, T minus 1 that are in the left of our target word, and T plus 1, T plus 2, T plus C, the words that are in the right of our target word. So in other words, the objective will be this here, this sum of products from of WT transpose, that is a transposed version of the vector WT of our target word, and the sum over the context of these V words that form the context of that word. So this is the objective of CBOW, that is the opposite of skipgram. So here we have a graphical illustration. So in CBOW, we have the context, we know the context, WT minus 2, WT minus 1, WT plus 1, WT plus 2, and we try to use it to compute the probability, or to compute the probability of observing our WT vector, like the vector of the target word. So the opposite of skipgram, let's say. Okay, so now these methods worked very well. Like they were developed, both skipgram and SIBO were developed in 2013 from Google researcher named Thomas Mikolov, who was the main contributor, main author of the respective paper, and they worked pretty well. And also they also constructed the word embeddings of Google News. It was a huge collection of 100 billion words. And they work really well, and they started to be adopted in NLP, like started to be used in different NLP tasks. But they had some drawbacks. They had some problems, let's say. One of the problems was the fact that these methods computed the word embeddings of words in a dense representation, like 300 dimensions, 400 dimensions, 500 dimensions, but they didn't account for the inflection property of the languages, which means that in different languages, a word like a noun, for example, can appear in different forms, like can appear in a singular form, like the dog or the cat, or in the plural form, like cats. So in English, these changes, like inflection properties on English, are not very high, in the sense that not many words change a lot. Like, for example, we have the verbs that are conjugated in a simple way, like I play, you play, he plays. Only an S in the third case changes the verb. So there is not a lot of change, let's say. Or when we the gender, for example, is not really, doesn't change. The words have the same form in different, masculine and feminine is not that significant. Or let's say the plural is formed in a simple way, like the cat and the cats, like just an S at the end. So English language doesn't have a lot of inflection, right? And SIBO and skipgram worked well because they were used for English language, and they worked well because each word vector, let's say, captures that word, and there are not many forms of that word, like but in other languages, for example, the German language or Hungarian language or many other languages, a word can change, can have many forms, like can have, for example, indefinite form and definite form, singular form and plural form, and the words that let's say have many forms, many representation that appear in the text in different forms. And this way, when we train the word embeddings with SIBO and skipgram, we only learn one of those forms or two of those forms that are more common in the training, during the training. But then when we use these representations in real in the NLP tasks, it may happen that during the fine tuning, during when we use these words in the task, it may happen that we encounter a form of those words that we haven't seen during training. And this is a problem. Like, this is called out of vocabulary word, the word that we haven't seen before, and for that word the network doesn't know what to do, so we just tag it as out of vocabulary, but it's a problem, like, that hurts the performance. So this was a problem, let's say, a limitation of SIBO and skipgram that were developed, because they didn't account for the different forms of inflective forms of a language, of the words in a language. And there were many, let's say, out of vocabulary words, so different words that were not seen during the training, because they are different forms, like cats, for example, the plural of a noun. Or in other languages like German, there are many other forms, let's say, that were not seen during training. And for this reason, SIBO and skipgram did not work very well with other languages that have a high inflection, let's say, high entropy of words, different forms of words. So for this reason, there was another method for learning word embeddings that is called FastText, and was developed by Facebook's research team. So now, what is the idea here? The idea here is that to avoid these out of vocabulary words, we will try to embed in one word vector not only the meaning of a single word, but also the meanings of the other forms of that word. For example, if we have the word remuneration, we will not try to capture only in the vector, in the W of remuneration, we will try not to capture only that word, but also different forms of that word, like subword units that I also called subword units. Like, for example, remunerate is similar, like orthographically is similar to remuneration, or iteration, because it has the same suffix, like remuneration, iteration. They are somehow orthographically similar, or consideration. So we will try to use all of these different subword units in fast text. They try to use all of these subword units, like based on the prefix, suffix, and the stem, the root of the word. They try to say, let's say, capture in the same word embedding, in the same vector, the meaning of different forms, let's say orthographic forms of the word. So here now we have another objective, another, let's say, representation. So for the predicted words, for the words that we will learn, WI, the word vectors, the respective vectors that we'll try to learn, we will try to capture vectors, like we will try to capture the meaning of different forms. So for example, we will have this set of n-grams, like n subword units. For the remuneration, we will have all the forms that start with RE. Then we will have REM, like REM. We will have all the forms that start with RAEM. We will have the root, let's say, that could be munerate or somehow. And we will have also different forms that end with some suffix, like ration or ation, let's say. So we will account for all of these subword units, and normally we will get the set of it, like we will avoid repetitions, like we will have the unique forms. And with these unique forms, we will try to embed all of their vectors in one vector, let's say. So for example, for the word that we'll try to learn, we will have a basic form. Let's suppose that it is remuneration. So the UI is the vector of remuneration. And we will also have all of these sums of the other vectors that are the different forms, let's say, different subword units. And we will try to normalize it by dividing it with the number of with the different subword units plus one, which is the basic word. So this will be the new representation of every word. Every word will represent not only itself, but also the different words that are the different subword units or different forms of that word in a certain language, right? And this is also in the case of known word, we have the known basic word and the different subwords. In the case of unknown word, we have only some subwords of unknown word. So this is how now we define the objective, like, of the words that we're trying to learn with fast text. And then for the rest is the same as skipgram, right? So we use the same method that was skipgram, but with the new definition of the word vector that is not just a word vector, but is the sum of all of the subword units of that main word. So this was the idea of FastTech. And practically for the different languages, we have, let's say, 3 to 6 grams or subword units for every word. We have, let's say, different forms, but this is actually language dependent, because, as I said, some languages are very inflective, highly inflective. So for some languages, for every word, we can have on average 10 forms or 20 forms, like they are very anthropic, very inflective. For some other languages, like English, it's just 1, 2, or 3 different forms, like because the words don't change that much. So yes, as I said, the idea of FastTech was to replace the new definition of W, like this definition here of W, in the training objective of skipgram, in the same methods of skipgram, and to change the training accordingly. And this way we will get new vectors that are better, let's say, because they represent not only a single word, but different forms of that word. So these were the 3 main methods, like SIBO, skipgram, and FastText, the 3 main methods for computing word embeddings. There are, of course, other methods that are developed, like, for example, Glove, that is based, based on the different occurrences of the different words, like it constructs a co-occurrence matrix of terms, like terms that appear together, and somehow computes the vectors. So there are also, yes, other methods, but these 3 are usually very popular. And they after when they were started to be explored by the different researchers, the researchers saw some different properties of these word embeddings. So as we know now, these word embeddings are, let's say, projections in a dimension, let's say, multi-dimensional space, a space of 300 dimensions. So if we make that projection and squash it in 2 dimensions, like from 300 dimensions, if we reduce it to 2 dimensions, for example, with principal component analysis, that is a technique for dimensionality reduction, we see different nice properties of these vectors of different words. Let's say nice linguistic properties, for example, semantic word analogies, synthetic word analogies, logical word analogies, and other interesting aspects that we see in this space, in this reduced dimensionality. Let's say in 2 dimensions, in a plane of 2 dimensions, x and y, we see different properties that are captured by the vectors that are trained with this word embedding tactics that I mentioned. So now here we have some nice, let's say, algebraic operations on the respective vectors that show us these different, these nice, let's say, characteristics, these nice analogies that are captured by the vectors. So, for example, if we compute, if we have the W king, that is the embedding, the vector of the word king, and we have the vector of the word man, the vector of the word queen and woman. So if we perform this operation, like if we, let's say, if we take king minus W king minus W man, so we see that it is a value that we get that is almost the same as the W queen minus W woman. So this is a gender analogy, right? It's an analogy between king and king man, let's say the masculine ruler and person, and the feminine ruler and person. It's a gender analogy. And it is because this queen man, like they appear in the different context windows in the training text. So when we learn the embeddings, they appear together in context windows that that make it possible to, so that when the embeddings are computed, their values, let's say, show this property, like the fact that the distance between the vectors are somehow similar, are somehow the same. And the analogies are different types, not just gender analogy, but we have analogies like logical analogies. For example, analogy of states and capitals, like the vector of Italy minus the vector of Rome, having a value that is similar to the vector of Austria minus the vector of Vienna, or other, let's say, other types of logical analogies, like analogy between a country and its currency, like Britain and pound, Russia and rubla, or other synthetic analogies, because the words the different forms of the words, as I said, tend to appear in the same window also. It's like, for example, a verb like catch and the gerund like catching. So vector of catch minus vector of catching appears to be similar to the vector of jump and jumping, because they are different verbs, but also the different gerunds are similar. And also the adjectives, like adjectives in the pure, in the simple form, and in the comparative form, like strong and stronger, and another adjective like long and longer. So again, we have these analogies, and they are captured very well in the dimensional space of the word embeddings that we have trained. So now, given these word embeddings, there are different ways how we can utilize them for our purposes. Like our purposes are to solve different NLP tasks, like to train models that solve tasks like, for example, topic prediction, topic recognition. Like we have different documents of different topics, like politics, economy, science, sport, and we want to train models to recognize the topic. And we can use the word embeddings and representation in different ways. Like we can try them on the fly, we can train them on the fly on the corpus of the specific task that we are trying to solve. We can train them on different corpora and then use them on our task. Or we can also retrieve, let's say, collections of pre-trained word vectors. As I said, like the developers of the word embedding techniques also provide some pre-trained vectors. Like the Google research team gave us the word embeddings trained on Google News, or also the Facebook team gave us the FastTech embeddings trained on Wikipedia. So we have also this big collection that we can make use of. And obviously, these different possibilities offer different advantages and disadvantages. So for example, when we train on the fly word embeddings on a specific task and on a specific data set, we will use this embedding layer. Usually we use an embedding layer that will learn the embeddings, the word embeddings on the data set, on the corpus that we use. And this embedding layer is now available in the different deep learning frameworks, like the two most popular ones, like PyTorch and TensorFlow, and they offer this layer, the embedding layer, for training. It is usually the first layer of a neural network that we build in PyTorch and TensorFlow, and it captures the embeddings of the words that we have in our dataset, in our training dataset. So when we use this method, we train directly on the task, and then the following layers will do like the topic modeling or the sentiment analysis and the other functions that we want the model to perform. And this method has the advantage that we get the vectors in the corpus that we want, and then we get them with the parameters that we want, because the embedding layer gives us possible parameters for training the vectors, different hyperparameters, like the dimensionality, for example, is the main parameter. So we can obtain vectors of 200 dimensions, 300 dimensions, 400 dimensions, and other parameters. So these are the advantages, like the fact that we will train it in the corpus and task that we want, and we will train it with our parameters. But one disadvantage is the fact that when we train it on the fly, we do not save the vectors, like we just use them for the task, and we do not reuse them for other tasks, for example. So this is a drawback of this possibility. Another possibility is that we train our own vectors on a corpus, and then we use these obtained vectors, we use them on different tasks. And for training them on a corpus, like there are different corpora available, text corpora available that are free in the internet, like book collections or Wikipedia collections. And there are also software packages or frameworks that we can use to train on those text collections, to train the embeddings. One of them is, for example, GenSim word2vector. Here there is a link here. I will illustrate its utilization later in the slides. So now if we train our own vectors on some corpus, we have the advantage that we train them as we wish, because this method, like the GenSim word2vector function, gives us the possibility to put our parameters that we want, like to train on the parameters that we want. So we train on the corpus that we want and with the parameters that we want. And another advantage is the fact that we can use these embeddings that we learned. We can use them in different tasks, not just one task. But there is a disadvantage that the training process can take a lot of time, because usually when we do this, we train on big corpora. So it may take a lot of time and resources, which we might not have. Right. So this is a possible disadvantage of this method, this possibility. And another possibility is that we train that we use the different word embeddings that were derived by other scientists, like for example the Google team or the Facebook team. The ones who used who developed this word2vector and fast-tech methods, they also gave us the possibility to use their vectors. So we can retrieve those vectors, not train them ourselves, but retrieve them as vectors that they are, and use them in our tasks. And this way, like, we have an advantage that we use vectors that are trained on very big corpora, because as I said, Google News was trained on 100 billion tokens, like huge amount of texts. We don't need to use the resources of our computer to train them again. And we can reuse them in different tasks and as many times as we want. But there are like two drawbacks. First of all, like the source text that they were trained on were kind of generic. For example, Google News was trained on news texts. And if we want to use it in another task that is, for example, sentiment analysis, there may be not enough relevance between the source texts and our text, our target text, let's say. So there, it may be that maybe it can hurt the performance, like, because there is not a big relevance between the sources and the targets, like the topics, let's say. It can hurt the performance. And also the training parameters that authors use to train their word embeddings may not be the ones that we want for our task. So these are two drawbacks that we can consider when trying to choose this possibility, like to use the pre-trained vectors. So for your curiosity, examples of pre-trained vectors are the big collection, like the GLOVE Common Crawl that is available here by Stanford's research team. And as I said, Google News that is available in this link, that is also a possibility, like a big collection that we can use. So one idea, one factor that makes possible to use pre-trained word vectors in different tasks is the fact that is the knowledge transfer, let's say. The knowledge transfer means that when we train these word vectors on unlabeled corpora, big corpora of texts, they capture some let's say some features of knowledge of some knowledge, let's say, of language in general, that is possible, that is let's say relevant for different tasks, maybe not very relevant, but somehow relevant. And now here it is possible that we can, so when we use this word embeddings, we have two possibilities. Like we can fine tune them on our downstream tasks, like we get the embeddings of Google News, and we can choose to change them, to update them a little bit when we fine tune on our, let's say, topic recognition or sentiment analysis, or let's say name entity recognition task, so that they learn some new features of the task, like more specific to the task. Or we can also choose to freeze them, like to keep them as they are in their own values, original values. So we put them in the embedding layer, and we put a parameter in the embedding layer, freeze, like not to tune them, and we use them as they are. So these are also two design choices when we use the pre-trained word embeddings. So the word embeddings, as I said, like the first ones, skipgram and SIBO, were developed in 2013, and they started to be used quickly, like in different tasks. There were some papers that were released in 2014, like quickly after the release of word embeddings, that explored their performance, like performance of using word embeddings with different tasks. For example, MR here is movie reviews, and the task was to predict the polarity of the movie reviews, like positive or negative. And there are also other tasks like subjectivity analysis and other tasks that they were explored. And there were different strategies, as I said. So first of all, the baseline is always to randomly initialize the word embeddings, but not to put any logic, like just just get some random numbers and make them as a vector of each word. Another possibility is to use the pre-trained word embeddings, but frozen, in the sense that static, so not to fine-tune them on the downstream tasks. Another possibility is to use the pre-trained word embeddings fine-tuned, like fine-tuned, retrained, let's say, on the different downstream tasks. And another possibility was to use a combination of the static and dynamic fine-tuned embeddings. And it was observed that fine-tuning them on different tasks usually performed better in some tasks, but of course not always. So these were some initial observations of utilizing word embeddings in different tasks. So now I will try to illustrate how we can train the word embeddings ourselves. So I chose the GenSim library, which is very nice, like because it's easy to use. It provides a simple to use API, like with function calls and the different, let's say, parameters. Yes, it is as a library. It's used usually for topic modeling and also information retrieval and that other, let's say, it offers different possibilities, but now I will use it only to train the word embeddings. So I chose texts from Game of Thrones books. There are 5 books of Game of Thrones, but I put them together in one bundle. And I will train them using the 3 methods that I just talked about, like SIBO, skipgram, and fasttext. So here we have like some code that is available in a notebook, but I just put it here for easier illustration. So first we will try. So if we want to train these word embeddings, first we will import some libraries, some packages in Python, like different normal packages, like NumPy, for example, that you should know, an LTK corpus that has this list of stop words in English language. The stop words are words that do not usually carry a lot of meaning, like articles and some other words that we usually remove from our word corpora when we try to work with texts. Like we don't really need them, so we remove them to let's say, decrease the computational complexity of the task. And then we have the send tokenizer, that is a function that is used to tokenize the text in different sentences based on punctuation, like full stop or question mark or something like that. And then we have the GenSim library that we will use here. GenSim models, we import word2vector that contains skipgram and SIBO, and fasttext, that is for fasttext. So here it's like a seed for reproducibility of the results. So we just set a seed of these random number generators, so that if we run our scripts multiple times, that will give us the same result. Now here we have the set of stop words for English language. So yes, the importables here. So set stop words dot words English will give us a collection of words like the, or him, her, some probably some articles that are in English language that are not very relevant in the text, and we will try to remove them so that we decrease the vocabulary. Now here we have a function that is used to get the words from the text, like to remove the, let's say, the noisy symbols. So here we get it's just a list of so we invoke this filter method on a lambda function that will only give us the words not in the stop word set, and then we have another regex here that will give us only the words. Like, so these b's are the boundaries, these w plus are only, let's say, ASCII text words, like not other symbols, let's say messy symbols. It's just a function that will clean up the text, will give us the words, set of words. Then we have another function for the word for the processing, like of the different sentences. So here in the file input name is just the file that I used for the book of Game of Thrones. So we open the file and then we go on line by line. We strip, let's say, the ending of the lines and then the lowercase everything to reduce the dimensionality, the vocabulary. We also use this trick here, line encode, ASCII, ignore, decode once again. So we use it to remove the non-ASCII standard symbols. And then we use the function that I mentioned in the previous slide, get words, to get the different words from the collection of sentences. So here this tokenized line tokenizes every line of text in different sentences, because a line usually contains more than one sentence. And at the end, like, we will also get the words that are of length more than one. So we won't get just letters because they are not real words. We will put them in this collection of sentences. And sentence words will be a list of lists. So a list of sentences, and every sentence is a list of words. So this is the, let's say, the text preprocessing that we will use in this example. So now here is a part of code that trains the methods. So here we have just one input file that is a book. It's actually a collection of 5 books, but I put them together for simplicity. Then we have this Game of Thrones sentence words. That is the call of this function in the previous slide, the big parse sentence words function in the input file. So it will give us the collection of sentences and words of the text. And then here we have the 3 main calls of the methods of the models. So CBO model is word to vector model. So we call this word to vector from the GenSim framework, the GenSim package. So here we have some parameters now, some important parameters. The sentences will be got sentence words, like the collection of all the text that we have after we clean them. Another important parameter, vector size, is 300. So this is the size of the vectors that we will obtain, so the dimensionality, let's say, of the vector space of all the embeddings that we will have. Now, window is another important parameter that I mentioned. The window is the context window. So the number of words in the left and the number of words in the right of every target word that we will use. So SkipGram, CBO, and FastTech use this window, this context window, to learn the words, to train the words. Min count is another important parameter. It means that we will consider only the words that appear at least 2 times in the corpus. So we will ignore the words that appear only once. So we use this trick this is, let's say, a feature selection trick, so that we focus, let's say, our computation efforts in the words that are more common and more frequent and more relevant in the text, let's say. So we avoid some words to decrease the dimensionality and to, let's say, lower the computational stress that the computational complexity in our computer. And the last parameter is SG, like skipgram is 0, because here we will use the CBO method. So CBO method is used if we set this parameter SG equals to 0. In the other case of skipgram, we just set it to 1. So SG1 means that we will use skipgram method. SG0, it means that we will use the CBO method. So these are the main parameters, and of course there are other parameters that can be used. So everyone can just check the API, the GenSim API. It's open source and it's available, like, in the internet. So you can see more parameters here, training epochs, for example, or if we want to use all the cores of our computer, we can put another parameter here, workers equals to, I don't know how many cores or threads you may have in your computer, so you may want to use it also. So there are other parameters, but this I'm just focusing here in the main parameters. So the same for skipgram. So skipgram word to vector sentence is the same set of sentences. Vector size, I've used the same dimensionality for both methods. Window, I also use the same window and min count, but here the only thing that changes is SG1 because we will use the SG. And in every case, we will save the vectors. We want to save them in some text file. So we have this call here, SIBO model, word to vector save, word to vector format. And then in the format, we put the name of the file in which we want to save them. Like here I used got.sibo, like Game of Thrones sibo.txt. And if we want to save them in text format that is easy to read, we just say binary equals to false. So we don't save them in binary format, we save them in text format. The same for skipgram, the only difference is this here, like SG1. And for fast text, we have this fast text function. And the parameters are similar, very similar. Sentence got sentence words, vector size, I use the same dimensionality, 300. Context window the same, window equals to 4, min count the same, 2. And then the same function for saving them. Work to vector save, word to vector format got FT for fast text, and binary false to save it in text format. And now this is what we got. So now we will try to perform some let's say one thing that we can do with GenSim framework is to compute the similarities between different words. Here, for example, we compute the similarity like SIBO model, like we use the SIBO model to compute the similarity like most similar, the different similar words with the word that we give as the parameter. Like here I have given the word king. And top n 15 means that we will try to get, like the model will give us the 15 most similar words to the word king. And it is based on the cosine similarity between the vectors. So the model will compute the vector of word king. And then we will compare it with all the vectors, other vectors of the words that it has learned, and it will give us the vectors of the words and the vectors with them that have the cosine similarity higher with the word king. And here we have the output, like king is very similar to kings, and this is the similarity, cosine similarity between their vectors. Baratheon was one of the kings in the book and the movie. Sun, Stannis, another king, I guess. Robert, another king. So different words that are very similar, that have similar vectors to the word king. This is what we get from SIBO. So if we use skipgram, we get similar, let's say, similar results, like only slightly different. On Sun, Stannis, here we have Aerys, here, like, let's say, similar vectors, similar words, because they are similar as methods, as I said. But if we use skipgram, we get different results actually, because skipgram, FastTech is more inclined to find similarities between orthographic words, like different forms of the same word. So here for king, we get kings, kingslaying, king's prior, kingdom, kingly, king beyond. So we get words that have some orthographic similarity with king, right? Because it uses a prefix, suffix, and the root. So this is why FastTech gives us these different results, actually, because it's a different method. And as I said, it's more useful for languages that are inflective, to account for the inflection property of the language. Okay, so is there any question up to this point? So here we conclude our topics, our word embedding, let's say, part of this talk, and we will switch to another part that is different, the transformer architecture and the different pre-trained language models. So if there is some question up to this point about word embeddings, I'm happy to take it.
Dear participants, if you have any such query, then you can raise your questions now.
I mean, you can also ask at the end, but since we changed topic, I think maybe some of you want to ask now about the word embeddings. Otherwise, I can continue with transform architecture and the pre-trained language models if there are no questions.
Dr. Çano,
okay.
That I guess we don't have such questions, so that you can carry on further.
So I can continue with transformer. Okay, so some context about transformer architecture. It was actually a very big development of the recent years. It was developed in 2017 by the Google research team. And it's encoder-decoder architecture. Like there are two, let's say, parts, like the encoder part and the decoder part, and it was primarily developed for machine translation, for, let's say, sequence-to-sequence tasks. And sequence-to-sequence tasks are tasks that try to match an input sequence of words. In general, any kind of input sequence, but in the context of NLP, it's a sequence of words. And in the more specifically for machine translation, we have sequences of source language, sequence of words in a source language, for example, in English language. And the model will try to match them with a sequence of words that are the translation of that English sequence, like sentence or paragraph, in some other language, like German or Hindi or some other language, let's say. So this was the main task, the main objective, the main reason why Transformer was developed as a sequence-to-sequence model, more advanced than the other sequence-to-sequence models like recurrent neural networks that were used before. So this was the yes, the reason. And the input, so we have the, let's say, input sequences, and then at the end we have output sequences that are computed from the probabilities, their respective probabilities. And the encoder, that is this left part, encodes the input sequence in some, let's say, encoded representation, let's say, numeric representation. And the decoder will try to let's say, to decode the encoded representation and to give us the output sequence. Like so from the sequence, input sequence in English, it will give us output sequence in Hindi language, let's say. So this was the main role of the transformer architecture. Like the details, the implementation details go beyond the scope of this talk, so I won't cover any of them, but you can of course check them yourself. And then after the transformer architecture that was very successful, as I said, in machine translation, there were a sequence of other, let's say, models that were based on its parts, like either in the encoder or in the decoder part of transformer. And they were based on this encoder or decoder to learn representations of words by using big collection of texts normally, and to learn, let's say, some knowledge, to learn knowledge from this let's say, texts based on these two parts, like encoder and decoder. The first big advancement was GPT. It was called GPT, generative pre-trained transformer. And it was used to generate text, like for generative tasks. Like, for example, when we want to have the ending of a sentence, let's say, we have some words, a sequence of words, and we want to know how the sentence ends. We use the generative models to end the sentence. Like, they learn how to end sequences of words. So they normally, let's say, they are trained on different, let's say, sequences, like a start, a text, and then then they try to let's say, to predict some to predict something, like the similarity between different texts or multiple choice. They were trained also to solve multiple choice tasks, like to choose a word as the best candidate of some other word or some in some context. So their, let's say, the architecture details of GPT are given here. Like it was developed in 2018. So as I said, using the decoder of the transformer architecture, the decoder part. So the objective of GPT was actually a language model, if you remember the definition of a language model. So it was trying to, let's say, compute the probabilities of a certain word given a sequence of words. So it was just trying to match the probabilities, so let's say, probability of a target word given a sequence of words. And using so these are some details, let's say. I don't really want to let's say, I'm just skipping them. You can read them in the respective paper, the paper of GPT. So as I said, the objective was to predict, let's say, this sequence, as in every language model, the objective was to predict the sequence of words, like the probability of finding the sequence of words, or in other words, to compute this, you know, this the sum of log probabilities of the different words, like UI given UI minus K, UI minus I given theta parameters. And the authors trained this model on a big collection of books, like a free book corpus, that is the free collection of books. And the model was trained, and it was very good, like in predicting, let's say, the continuation of the ending of sequences. so when they fine-tune the model, so when they pre-train the model in the book corpus, but then they also fine-tune the model in some other objective, like in some other smaller data set for some other task, like for example topic recognition or something like that. And in the fine-tuning phase, the learning objective is different. So in the training step, we have n sequences of words, like from U1 to UN is, let's say, the unlabeled sequence of tokens, unlabeled sequence of words in the books. Now here we have another data set of M samples that could be, let's say, different, I don't know, movie reviews, for example, that we want to predict the emotionality. So we have this second learning objective that is computing this log probability of Y. Like if we try to classify, for example, to predict if a movie review is positive or negative, then this Y will be 0 or 1. So we will try to compute the probability of Y being 1, given a sequence x1, x2, x3, xm of the input samples, right? So of the training data set. So this will be the new objective, and then combining the two objectives, like the first that was the pre-training, let's say the objective of predicting this category, with the objective, the first objective that was that was this one, like to predict the next sequence, let's say. They so the authors combined these objectives and then fine-tuned GPT. And after fine-tuning GPT, they used it in different benchmarks. And they saw that it was actually in the state of the art. It reached new, let's say, state of the art scores in different tasks. These tasks here are part of are part of the let's say different collection of tasks that are used in NLP to let's say to evaluate the language understanding problems. So now this was the GPT, like a development of 2018, the first pre-trained, one of the first pre-trained language models. And then another very popular that became a model that became very popular was a BERT that used not the decoder part of the transformer, but used the encoder part of the transformer. So the left side of that image of transformer, that is this one. And it was, so BERT used the encoder part of the transformer, and the idea was the same. So BERT is bidirectional encoder representation from transformers. And so now one advancement, one new thing of BERT is the fact that it is bidirectional. So GPT was trained left to right. So it goes in the training texts and goes from left to right. It sees the sequences of text that we have in the left, and it predicts the right word. So this is the language the objective of GPT. Now BERT is bidirectional. And that's why it somehow worked better in some tasks. So it introduces self-supervision, some advanced concepts that are part of transformer architecture. So I'm not, again, I'm skipping them here. Here we have some parameters about its size. Like there were two models derived with different transformer blocks. There was BERT based with 110 million parameters, and BERT large that was 340 million parameters, like larger because it was trained on more data. So now the idea of BERT is to use a masked language, to use the masks of different words. Like the training objective of BERT is to go left to right. For example, here we have the sequence that is popular, like the quick brown fox jumps over the lazy dog. So now the idea of BERT was to mask some of the words in the sequences, in the pre-training sequences, and have the model try to predict which are these words. So in BERT, the authors took 15% of the samples and then replaced some of the words in these samples with a mask. Like, for example, here we have just a mask, a special token, let's say. And the target of the word, the targets of this mask are fox and lazy, because this is the sentence, the original sentence. So the model was trained to try to predict these masks of the input, try to find the real words that were after the masks. So to account for some problems that were during the pre-training, they observed that it's better to predict, let's say, 50% of the tokens in the samples, so 10% of the selected tokens in the words. Like they used let's say, transpositions and also substitutions. Like for example, in some cases they use the real word fox. In some cases they use just some other word like went in the stand of the mask, so that they had to optimize this training objective of the model. And this is how another, let's say, task was. So that the first objective, let's say, was to predict the masked word. So they masked the words and try to predict it. And another task they used to train objective, let's say, used to train BERT was to find if two sequences or two sentences follow one another. For example, we have one sentence that is the fox is quick, and then another sentence, it jumps over the lazy dog. So now they again mask some of the words and try and train the model to try to predict if the second sentence is comes after the first sentence. Like this was another the second objective. And here we have this CLS, which are the let's say which is just a separator for the sample, like indicates the start of a training sample, and then the SEP, which is separates the different sentences from each other. So this was the second objective of BERT, and they put them objectives together. So the objective, like the combined objective, was the loss of the neural network, was the loss of the masked language model plus the loss of the next sequence prediction. So the second task was next sequence prediction, predicting if the second sequence is comes after the first sequence. And of course, they used also, like, they pre-trained with different parameters, like sequence lengths of 128, or also bigger sequence lengths of 512, because in the case of predicting if a sentence comes after another sentence, the sequences are longer, so that's why they used two sequence lengths. And after pre-training BERT, they fine-tuned BERT, like the same model with different data, like of a downstream task, like for example, sentence pair classification tasks, or a single sentence classification, question answering task on the respective data set, that is SQUAD, that is a popular data set for let's say question answering, or single sentence tagging, like tagging a sentence with different categories, or words, like say name entity recognition is a task. So there are different tasks that they fine-tuned BERT on. And fine-tuning was somehow simpler. Pre-training BERT was very hard, like it took many days and many resources. Fine-tuning BERT with some, let's say, parameters like batch size or ADAM optimization and dropout with different parameters was not that hard. It took less time for each task. And at the end, they again evaluated BERT on this GLUE benchmark. GLUE is generative language understanding evaluation, like a set of benchmarks that try to evaluate the different models, like different tasks that you see here and different scores that they saw. And of course, BERT Large, the biggest version of BERT, broke all the records, all the state-of-the-art scores. And that's why BERT became so popular, like became a very, very popular model that is used today in many tasks, in different downstream tasks. And it's so popular that there is also common to say BERTology to the field of study of BERT and utilization of BERT derivatives of variance in different tasks, like because all the many models were based on BERT that came after. And so now here we have some derivatives, some different models that came after BERT, and they somehow try to improve BERT in different aspects. So for example, Roberta is a model that was based on BERT. And the authors of Roberta saw that BERT was not fully trained, like in the original form. Like so they changed the masking strategy of BERT, like as I said, masking different words. They used dynamic masking in the sense that they multiplied the different input sequences. They used the same sequence several times, but with different masking. So in the first, let's say, collection of texts, we have a certain masking of some of the words. In the second version of that same input sequence, they masked different words. In the third, different words. So they used 10 of this. For every input sequence, they used 10 versions with different masking. And that's why it's called dynamic masking. And they trained it. So they trained it, and obviously it was a bigger model because it has 10 times more, let's say, training samples. And yes, I mean, it is bigger in size and it took more resources to train, and it performed. They saw that it performed better than the BERT. So here we have the main difference between BERT and Roberta. So in BERT there was this let's say masking that was static, like one way to mask the different words, and also the training epochs were 40 for the total corpus. In Roberta, they multiply the training corpus 10 times, and they use these different maskings in all of these 10 versions of each of the training inputs. And once again, they used 40 epochs. And so, yes, they got a Roberta that is a bigger version. That was a bigger version of BERT, and also, let's say, worked better than BERT, the original BERT, in many tasks. So here we have some scores in the same, let's say, set of tasks that are used to benchmark BERT. So once again, and there's this comparison between different models: BERT large, XLNet large, that is a different model, I will mention it, and Roberta seemed to be the best model. So it was a big improvement, let's say. And of course, many other models came after Roberta, like Albert, which is, let's say, which tried to, let's say, be more efficient, let's say, from the computational point of view. Also, DistillBERT tried to distill, let's say, to get the same results of BERT, but with less computational resources and a smaller size, let's say. There was also another model, Electra. All of these models that are in this slide are based on the encoder architecture of transformers. So they use the encoder blocks. Electra is a different model that tries to use the, the generator and discriminator approach, like in GINs, if you know, like generative adversarial networks. So the generator, generates the masks and tries to predict the words that are after the masks, and the discriminator discriminates, like says, tries to find out if the word that the generator put for the mask was the real word in the input corpus or not. So it's a different strategy that used, and they showed improvements over the significant improvements. And there are also other models like Ernie, that I think Ernie was a model from Baidu, like the Chinese search engine company that provided improvements in Chinese language. And then Big Bird, that was from Google. It was trained to work with longer sequences, let's say, to model longer sequences of sentences, so for some other special task. So these were the models that came after BERT that were based on the encoder architecture of transformer, and there was also some models that were based on the decoder architecture. As I mentioned, GPT-1 in the beginning, GPT or GPT-1, and there were also some, let's say, newer models, bigger models, GPT-2, that is like GPT-1 but bigger in size and trained on more texts. XLNet, that is similar to BERT, but doesn't use masking as training objective, but use permutations of word positions. And then GPT-3, that is today probably the state of the art today, like it's much bigger than GPT-2. GPT-3 has 175 billion parameters. And there is also a new model, a recent model called Bloom, that let's say is the open source version of GPT-3. Like it's similar to GPT-3, but it's open to the public. And I think it has it is a little bit bigger in size, like I think 176 billion parameters, but is open, is more open, let's say. It was trained on, they claim that it was trained on better filtered texts. So these were the different models that I put for this presentation. I tried to cover, let's say, not to go very deep because the time was limited. So now, if you have some questions, I'm happy to take them. And thanks for your attention.
Dear participants, now we are open for the Q&A session. So if you have any queries pertaining to this particular session, even for the first part or for the second part of this presentation, you all can now go for it.
So
I do repeat, if you have any sort of queries to ask, then you can go for it.
Good evening, all. I want to ask that if it is the application point of view, can this be applicable to any certain problems that you have done? I'm actually I am confused. That's why I'm asking.
once again, please, application of what?
Application of this NLP.
You mean application of word embeddings or pre-trained models or something? They are used today for all kinds of applications, actually, like sentiment analysis, topic recognition, machine translation. Like the biggest application is machine translation, and actually this task, like training models that can translate between languages, has been the driving force for most of the developers, like word embeddings, pre-trained language models, encoder decoder. So this has been the main application, like machine translation. But the models that were developed primarily for machine translation were also adapted for other types of tasks, like text summarization or other types of tasks. So the applications are very numerous, like as I said, but usually the most important one was machine translation, translating from one language to another, like having models that, and then machine translation quality. The quality of machine translation today has reached that of human translators, like, or even surpassed somehow. So the quality of machine translation has been greatly improved because of all of these developments that I tried to cover in the presentation, because of embeddings, pre-trained language modules, and other developments.
So for a beginner, how he will get the data to work to start this translation, like from any book?
You mean for machine
or
translation?
Any YouTube tutorial or any software?
So if you want to develop a machine translation model, there are already some data, some corpora, like with pairs, and you can start, let's say, exploring the existing models. They are all open source. Most of them are open source. There is this nice library, Hugging Face Transformer, that you can use, and you can also get different data, and you can fine tune their BERT or other models, and you can see their result in the different tasks, like translating from, because there are different corpora, like German to Hindi, English to German, English to Hindi, and other tasks. Then you can see the scores that you get, and then you can try to improve, like to go from Bert to Roberta. So Hugging Face has provided all of these pre-trained models, and they are very easily to use. Like you just get some lines of code, you download the pre-trained model, and then you will see the scores. So I suggest that you start with Hugging Face Transformer library, and you explore the different PLMs, pre-trained language models, on a certain task, like machine translation or some other task that you like.
Thank you.
Okay, you're welcome.
Any more questions? We assume that there is no more questions, I guess, from the participants' perspective. So now that is the time to propose a vote of thanks. Dr. Çano, that I'd like to extend my sincere gratitude for such an insightful and informative presentation. The slides you showed gave us a close look at the language model and how the text can be represented and also are being generated and predicted as well as classified through the transformer, encoder, and decoder architecture. Many audiences were at a standstill in their progress, and your talk seemed to provide much needed help. Thanks again for a truly productive evening. We hope you can join us again in our future endeavors. Thank you so much, Dr. Çano.
Thanks also from my part. It was a pleasure also for me. And I wish you success in the other sessions of this event.
Thank you. Thank you so very much, sir.
Okay.
So dear participants, so this is the end of this today's session, and hope that you have gained a lot of insights from this very lecture, and hope to see you tomorrow with a new learning altogether and with a new speaker. Thank you for your patience of hearing, and have a good night.